Alright, in determining whether or not a sampling method is taking two different variables and they're independent of each other versus two different samples or whatever, and they happen to be tightly wound or very dependent upon each other, we have to look at what we're dealing with. So if it looks like the sampling method of the first sample is tied directly to the sampling method of the second group, then we may have a dependent variable. So the dependent samples are referred to as matched pairs samples, and what we're looking for is something along the lines of, say, a before and after, or two things, anywhere where you're putting data into pairs as opposed to just randomly jumbling a bunch of data. So an example might be 50 people go on the Atkins diet, and they take their weight before they start the diet, and then they take their weight 6 months later after they've been on the diet for the 6 months. Those would be paired data. You're taking the same person or people and finding their before and after weights, so that would be dependent, something along those lines. If you're just taking trying to determine if the Atkins diet is better for men or women, you take a group of 50 men, you take a group of 50 women, and get their net change, then you're looking at something else. Alright, so here's an example. We're trying to determine whether or not this is dependent or independent. So a researcher wants to know whether the price of a one-night stay at a Holiday Inn Express is less than the price of a one-night stay at a Red Roof Inn. She randomly selects 8 towns where the location of the hotels is close to each other and determines the price of a one-night stay. So presumably, say Chicago is one of the cities that they're looking at. You've got a Red Roof and a Holiday Inn Express very close to each other. That is one of the pairs. Then you go, somewhere else in New York or suburbs or something, whatever you want. 8 specific towns where they're close. You're looking at paired data, so you have dependent data as far as what you're looking at. So each one can be matched with another from the other group. Now, our confidence intervals for matched paired data, this essentially turns into a one sample. What we do is we merge the before and after, or the two different data points, into one value and treat it as basically a one sample. So if we're dealing with a small sample where n is less than 30, we're going to use a t-distribution. This d with a bar over it is the value of the mean for the difference data. So if you've got one Red Roof Inn is $80, the other one is $75. If the first one minus the second one would give us a net positive 5. If the other one was larger, then it might be negative 5, that sort of thing. We average out all of the different differences, and that's what gets us a d bar. S sub d is the standard deviation of the differences, and n is the number of pairs, not the total number of data points. So we're looking for the number of pairs. So again, we use a t if we're dealing with a small sample, and we use the z if we're dealing with a large sample. Otherwise, you basically just run it as a one sample confidence interval. Now, if we're dealing with the testing of it, again, it's going to look very much like a one sample test with one exception. In the one sample test, we're looking at the mean equaling a parameter, or no, not a parameter, but some value, some proposed value. In this case, it's always going to be 0. So we're looking to see if there is a difference. So in this one, there's no difference versus there is a difference. So the mean of the paired differences equals 0 versus doesn't. In this one, we're looking to see if our first set of data was essentially less than our second set of data based upon a negative value, and here vice versa. We're looking at the first group being greater than the second group. And you can mix and match all you want. If you wanted to make Red Roof Inn 1, Holiday Inn Express 2, you could certainly do that and flip them around. Just make sure you put the sign in a proper manner. So like all the other tests, we're going to have to calculate the test statistic. The test statistic is exactly the same. We're using all the parts from the confidence interval. The mean of the differences divided by the standard deviation of the differences, which is going to be the standard deviation over the square root of n. If you're dealing with values of n that are less than 30, number of pairs less than 30 that is, we have a t, again n minus 1 degrees of freedom for that. And for values of n greater than or equal to 30, we deal with a z. So our critical regions will be determined based upon that information. A t, we use the t distribution to find the critical values. For a z, we use the z distribution. And again, if your test statistic is in the rejection region, then you will reject. Otherwise, you will fail to reject. And as always, our p-value method works. If the p-value is less than or equal to alpha, we reject. If it's greater than alpha, we fail to reject.